Hello and welcome back to a video series on MAC 1140 Precalculus Algebra. My name is Sean Perry. These are guided notes number 28 in the series, Final Exam Review, Part 2. So let's resume with question 23, which is on an exponential equation. We have 3 to the power of 6x minus 10 is equal to 5 to the power of 5x minus 9. And we see that these bases, 3 and 5, really aren't related through powers. This isn't like 3 and 9. So I wouldn't try to find any common base to them. We'll go through a couple different ways that you could proceed with this problem, but all of them are going to involve taking a logarithm. If we don't have a preference between base 3 or base 5, let's just take the natural logarithm of both sides. Since powers come out of logarithms as products, this will have the effect of bringing the 6x minus 10 and the 5x minus 9 out of the exponent. And then we're just going to multiply both of those things by the constants ln of 5 and ln of 3. And there's a few different ways we could proceed here, but let's divide over the ln of 3 to the other side. And because it's kind of a pain in the butt to write this expression over and over and over again, let's just call it a for now. We'll replace that with its exact expression later, but this will save us some space and time. So how would we proceed if this a was just any old non-zero constant? We would distribute that a, then take all of our x's to one side and all of our x's to the other side, same as any linear equation. Factoring out our x, we then have an expression here which we could divide to the other side. So this has isolated our x. We've now solved for our answer, and we could replace a with its value log base 3 of 5. This gives me both an exact expression and something I can plug into the calculator to get a decimal approximation. Another perfectly valid way we could proceed from this step is to not combine them necessarily, but just say that ln of 3, let's call that a constant b, ln of 5, let's call that a constant c. You don't really need to do this step, but it saves us some symbols since we don't have to write 1, 2, 3, 4, 5 symbols. We just write 1. We would distribute, regroup around x, so bring this 5c x over to this side and take this 10b over to this side, factor out my x, and divide this expression here, 6b minus 5, over to the other side. Rewriting things in terms of our constants, we do have an exact expression here, which would be a totally valid way of writing the answer. And plugging that in, we of course should get the same decimal approximation. Now, even if we hadn't looked at the decimal approximation, we could conclude that those two expressions were equal. In terms of our choice of parameters, a was just c over b. And so from this expression that we just had, from our second methodology, we could multiply on the numerator and denominator by 1 over b and get our original expression as before. And there's other ways we could have approached this as well. There was no reason that 3 needed to play the role of the base versus 5. But these are two good exact expressions for the answer and their decimal approximation. 24 is similar, so maybe pause the video and give this a check to see if you can do it, and then follow along. I'm only going to go through one of these methodologies for this one, and I just wanted to stress that we can in fact take any log we like of both sides, which will free up these exponents here. We could even take log base 2 or log base 7. That would be fine as well. I see no reason to hold preference, so I'll just take common log this time. This brings down our exponents, and dividing over log base 2, we get this expression for log base 2 of 7. Let's call that c. We could then distribute our c against these two terms and regroup our x's and constants. From here, we want to factor out the common x that's in each of these two expressions and divide over its coefficient, which gives us an expression. This would be our exact expression, or an exact expression for x, and we could get a decimal approximation by plugging that into the calculator. Question 25 is asking us to do some matrix multiplication, so let's do a little review of that. Remember, matrix multiplication, we're going to take the rows from the first matrix and the columns from the second matrix and use those to construct each entry in the product matrix. Now, that actually means that the number of columns of the first matrix and the number of rows of the second matrix have to match. The columns of the first matrix and the rows of the second matrix matching here will allow us to do the algorithm that's to follow. And the result will be a new matrix which has the same number of rows as the first one and the same number of columns as the second one. So for example, here, to get our first row, first column position, we take the first row of the first matrix and the first column of the second matrix, and we take the product of their terms going down the row and down the column, and then add those products together. It's a little bit easier to see when they don't match like these zeros do. Let's look at the first row, second column entry. That's going to be the elements of the first row, 3 and 4, times the elements of this second column, 3 and minus 4. We take their product, we sum them together, and we just keep repeating this to get each entry of the new matrix. We can also proceed to check our work on the calculator. Let's edit ourselves to 2 by 2 matrices. So here's our first matrix, matrix B, also 2 by 2, with entries as such. And with these stored, if I now say what is matrix A times matrix B, I can find my answer. Always keep in mind that in general, matrix multiplication is not commutative. Question number 26 asks us to find the inverse of this 3 by 3 matrix. The fastest method is to use a matrix utility, putting in our entries into, say, a TI-84 calculator. We now have access to a variety of manipulations we can do to matrix A, and finding the inverse, the command is to use the -1 exponent button. This will give us the reciprocal of the matrix as such. However, there's a variety of reasons we might want to know more about how to do this by hand, both theoretical and practical. Maybe you don't have a calculator. Here's a way of finding the inverse of the matrix that uses row operations, so we can review those at the same time. We can augment this matrix by appending another identity 3 by 3 matrix right next to it. And now what we want to do is perform operations that are going to put this in reduced row echelon form. That is to say, we want to move this identity matrix over here to the left-hand side. First, let's turn this 3 into a 0 by adding 3 times row 1 to row 2 and calling that our new row 2. Then let's turn this -2 into a 0 by taking 2 times row 1 and adding that to row 3. Now that's our new row 3. We now have a lot of stuff in place. Let's actually skip this second column. It looks pretty good. Let's go on to this entry here. We want that to be 0. So we could add -13 times row 3 to row 2 to get a new row 2. And finally, we just need to get this guy to be 0. So we add 4 times row 3 to row 1 to get a new row 1. And now we have achieved an identity matrix in this front 3 by 3 slot. And this then succeeding matrix is going to be our inverse matrix. Another method would be to use the adjoint formula. We could take the adjoint of matrix A and divide every entry by the determinant. Remember, multiplication by a constant against a matrix just brings that constant in against each term in the matrix. And so this is only going if the determinant of A is non-zero. So now let's go in and calculate the determinant of A. One way to get the determinant of this matrix is to expand by minors. I'm going to go down the first row. We could do 1 minus 0 plus -4. That's down this row, changing the sign each time. And then multiply by the minor here. This is going to be the determinant of the matrix that we get. If I were to delete the first row and the first column, we would get this matrix 1, 1, 0, 9. And so that's our minor, and then we take its determinant to get our cofactor. Same thing here with our first row, second column. This gives us a matrix. And first row, third column, this gives us our last matrix. So then we're down to taking determinants of 2 by 2 matrices, which we could do by taking the diagonal element here, 1, 9, and subtracting the diagonal product here, 0, 1. We repeat that for each matrix, and what we find is that we get determinant 1. That's kind of nice because 1 is its own reciprocal. 1 over 1 is going to give us 1. Then what we want to do is find the cofactor matrix. This is on the way to finding the adjoint of the matrix. Essentially, we have signs alternating along each row and column, and we then want to put the cofactor, or the determinant of the minor matrix that we get when we deleted the entry in, say, row 1, column 1. So you'll recognize these first matrices along the first row from what we just calculated for the determinant, but we're going to repeat that process for every entry. And taking these determinants, we would find this matrix here. Now, you might even recognize the elements of the identity matrix here. After all, we're going to scale by 1 over the determinant, but the determinant was 1, so these numbers are all going to stay the same, but their positions are going to change. And that's because the adjoint of a matrix is the transpose of the cofactor matrix. So we want to flip it across the main diagonal, interchanging the role of rows and columns. Once we do that, we get our inverse straight away. Number 27 asks us to find the solutions to this linear system, and you might already notice some of these look like multiples of the other. In general, to solve a system using matrices, we want to encode this as an augmented matrix. That's a n by n plus 1 matrix in this case, and that's going to have the following entries matching the coefficients from the system of equations up here. And then we can put this in reduced row echelon form. And we could do that with row operations, of course, but your test for the final exam will be timed. So we kind of want to use the most efficient method to solve it, and doing a sequence of repeated rote arithmetic operations, that's literally what the calculator was born to do. Let's check our entries, make sure everything looks good here, and then the command we're looking for is reduced row echelon form. So scrolling up or down until we get to ref, we're going to plug matrix A into that command, and we're going to then have to interpret the results. If you'd like to look at things in terms of a fraction, you could store your answer as a fraction, but it doesn't really matter. There's a couple issues going on here. The last row is all zeros. That's not so much of a problem. There might still have been solutions if the rest of things had worked out here. We might just have had an infinite number of solutions. However, in this middle row, we wind up with what would be 0x plus 0y plus 0z equals 1 if we write this as an equation. Now that tells us that 0 is equal to 1, which is in fact a contradiction. So we're going to not find any solutions to the system of equations when we have a row which looks like this. Even if we wind up with a row that looks like a tautology, this row indicating a contradiction is going to force us into a situation where we have no solutions system. Number 28 gives us a problem about two numbers. It says their sum is negative 20 and their product is 91. This is kind of a question we might have to ask if we were factoring a polynomial. But the time has come to see it as a nonlinear system. We've said that their sum is minus 20 and their product is 91. So how could we find that? Well, we could solve for y in the second equation, substitute that in for y in the first equation, and how do we solve something that looks like this rational equation? Well, we have to clear denominators, which means multiplying through by x. Then we want to, factor this polynomial, which would have a similar question system to the one that we were just looking at. What things multiply to be 91 and yet add up to be 20? And when we solve that, we get negative 7 and negative 13. And to find our corresponding y's, we would plug each of these solutions back into our y equals 91 over x equation. But that gives us negative 13 and negative 7 back. So what we see is that either I'm calling the first one negative 7 and the second one negative 13, or I'm calling the first one negative 13 and the second one negative 7. Those aren't really two distinct solutions. These are just our two numbers that have the property that they sum to negative 20 and have a product of 91. So these are our two answers. Question number 9 asks us to fit a quadratic model to a system of points. And there's a nice way that we can do that with matrices. Basically, we want to make a system of equations out of the information given. We know our model looks like something times x squared plus something x plus something, and we have the value of x and the output value y, shall we say, in three cases. Plug in 1 into this equation, we get 10. Plug in 2, we get 7. Plug in negative 1, we get 14. So with unknowns a, b, and c, we could write down these coefficients that we get when we plug in a value for x into this matrix as such. Putting this in reduced row echelon form and storing it as a fraction, we get the following output, which means my model looks like this. This is my a, b, and c respectively. Question 30 is a question about partial fraction decomposition. The first step here is to factor. Now we have a repeated root in y squared on the bottom, so we'll need a fraction over here with a number up top for each base, which ascends from having the first power to the nth power. Now that's only going to be two terms here, but if this had been a, say, y to the third power, we would have needed y and then y squared and then y to the third. We would need all of those in ascending fashion. And then we have another term for our y minus 3 factor, and this gives us three fractions, which we're going to want to find the numerators for. We could imagine clearing denominators. We could also imagine actually combining these fractions here and comparing their numerators. And what we would get is this expression, right? If I want to multiply on both sides by y squared times y minus 3, a single y will cancel here to give me this term accompanying the a. If I multiply by the same denominator over here on both sides, really, I would wind up canceling y squared, and we would get a y minus 3 on our b term. And finally, the y minus 3 would cancel from the c term and leave a y squared there. Let's solve this one using coefficient comparison. What we do is we expand and then regroup around y squared, y, and the constants respectively. Now over here we have a y squared, a y, and a constant term, and we're going to want to set those coefficients equal to each other, as I've indicated here. So this actually gives us a system. We know that a plus c must be equal to the coefficient minus 2, negative 3a, and b, which keep in mind we want to write these in their appropriate columns. That has to be equal to 6, and then negative 3b, this has to be equal to 9. If we were to solve the system by hand, I would definitely start with this one because it's the easiest one to solve for its variable. But really, let's just encode this as a matrix and then perform reduced row echelon form and interpret the results. This says that 1a is equal to minus 3, that 1b is equal to minus 3 as well, and 1c is equal to 1. So remembering where a, b, and c were in our original expression, we want to plug in minus 3, and 1 respectively. And that gives us our decomposition. Question number 31 is similar. We want to first factor the denominator and then split this into partial fractions. So the first thing I notice is that we could pull a y from every term. And then the second thing I noticed is that this remaining polynomial here could be factored as such. This gives me 3 terms, a, b, and c, with a y plus 5, and a y minus 2 in the denominators respectively. Now, because when we clear denominators, we had distinct roots here, and all simple roots, all linear factors, right? When we have distinct linear factors, I think there's a simpler method than using coefficient comparison that we could employ. So let's clear denominators, right? And then we'll have no y on the a term, no x plus 5, but the other 2 on the b term, and no y minus 2, but the other 2 on the c term. We can choose what value we substitute. By force of habit here, I have chosen x to be my variable. Let's keep it in terms of y. So if I choose y to be 0, that's going to have the effect of canceling the b and c terms because we'll be multiplying them by 0. Now over here, I don't cancel. I have 5 and minus 2 remaining, and that multiplied against a has to be equal to 20. How do I get 20? We'll just plug in y is 0 over here as well. And we could solve this equation to get a is equal to 2. We could repeat that with the other roots. For example, if I plug in y equals minus 5, over on the left-hand side, that evaluates to 105, and on the right-hand side, it has the effect of canceling the a and c terms, but leaving the b term as negative 5 times negative 5 minus 2. So this is going to give me 35, and dividing this over into the 105, negative, we get negative 3. Last, we have a root of positive 2 here. If I plug that in on the left-hand side, I get 42. And if I plug that in on the right-hand side, it cancels the first 2 terms, a and b, and gives me 2 times 2 plus 5, which is 14. So dividing the 14 off, we find that c must be equal to 3. And then reminding ourselves of what a, b, and c were, we can plug in the numbers that we got for them to get our partial fraction decomposition as such. Question number 32 asks us to find the determinant of this 2 by 2 matrix. It's highly degenerate. If I take the diagonal product here and I minus the diagonal product here, I'm going to wind up with 0. So amongst other things, we know this is a degenerate system of equations, or that perhaps the matrix A simply has no inverse. Regardless, this is a pretty easy determinant to take. You could also type that into the calculator if you felt particularly lazy, but a 2 by 2 matrix, you should be able to take that determinant almost in your head if the numbers are simple enough. Let's continue. Question 33 asks us to solve this system. So to solve this system of equations, I would first encode the coefficients into an augmented matrix. I would then put this matrix into reduced row echelon form, and then we really just have to interpret the results about x being equal to 2, y being equal to minus 3, and z being equal to 1. One of the nicest uses of matrices is to make short work of systems of equations like this, which we would otherwise have to solve through more arduous methodologies like elimination or substitution. Question 34 is similar. We take our system, we encode it as a matrix, we do that reduced row echelon form dance, and we interpret our results. Now, this is used to solve linear systems of equations, so we're kind of out of luck for that methodology when we go to talk about nonlinear systems, although there's some ways that we could consider this to be a linear equation in the variable x squared. Perhaps it's better that we simply take advantage of substitution or elimination methods in this case. For example, I could multiply this equation by -1 and add it to the first equation, or subtract them if you like, and this would have the effect of canceling my x squareds. Now that gives me an equation I could solve for y, and then proceeding to plug in that value for y, we could then solve for x, taking plus and minus the square root of 9 to get 3 and -3. And each one of these corresponds to a solution where y was equal to 1. So these are distinct solutions with a corresponding 1 for the y value of each one. 36 gives us another nonlinear system to solve. The way I would proceed with this one is substitution. If I solve this equation here for y and plug that in here, squaring both terms, we get the following. Now, multiplying through by x squared, we cancel the denominators and we wind up with a fourth power and a second power over here. Let's regroup, but also let's see that we have not a full quartic polynomial, but something in quadratic form. If I make a substitution, u equals x squared, we can see that explicitly. This is u squared minus 10u plus 9, which is something that I can factor and then solve those factors. Now, this then needs to be resolved for x. U was x squared, and so both of these terms give me actually 2 answers. So we have a total of 4 solutions for x. And from there, we want to go back to our equation of y equals 6 over x. Plugging in each one of those 4, we get 4 corresponding solutions for y, and so these 4 become our answers to the system. Questions 37 and 38 are about finite sums. So let's talk about how we might acquire these numbers. There's 2 ways that come to mind for me. Number 1 is to use a calculator, and 13 is a lot to type in by hand, so let's take advantage of the fact that your calculator TIs can do sequences. If I go to second, stats, that gives me my list options, and then over to ops, we see a button for sequences. Now, if you have a newish calculator, it will give you some prompts for these. If not, you need to remember that the order you need to put the arguments in is your expression, the variable of that expression, where it starts, where it stops, and if it's not going to just go up by 1, you can put a step size in. Ours are each just going to be basic sums where the step size is 1. We go 1, 2, 3 for k, and so on up to 13. So we could really leave that one blank. What do they want us to sum? Well, they want us to sum something cubed plus 9. The variable we've used here is x. We have to remind the calculator of that. Where does it start? 1. Where does it stop? 13. What's our step size? It's 1, so we could skip that part. And notice that this populates the command sequence with the values that we put into it. If you had a TI-83, for example, you would have to know this order and plug these in as such. And this is going to give us the values 1 cubed plus 9, 2 cubed plus 9, 3 cubed plus 9, and so on. What we really wanted to do is add them all up. That's what this symbol means. So let's go back into our list ops, and that would be the command sum, which we can find under the tab math. So in order to put that in without having to retype everything, I'm going to press enter to call my last entry, go back to the beginning, and insert the sum command. Now, you could also have just typed the sum command first in the first place, and this gives us our answer. We could do the same thing, sum of the sequence, looking like 4x to the power of 2, with variable x, and now we'll just start this at 9, end this at 26, with a step size of 1, and we're good. Here's some other ways that we could have calculated these if we didn't have a calculator, and we didn't want to do it precisely, arduously by hand, by plugging in 9, plugging in 10, plugging in 11, and so on, and going all the way up to 26. There's sort of an in-between. But in order to do that, we need to know a few things. So I've written those few things here. Here are some basic summation principles and properties. Number 1, summation is linear, meaning you can pull out constants from expressions of k, and you can distribute summation around addition or subtraction. One can also split up a summation going from 1 up to n by first going to an intermediate m, then picking up again after m plus 1 and moving on to n, right? This is just doing the sum in two phases, going up to m first and then thereafter up to n second. But this is an important kind of concept of doing the sum in two parts. And the reason is because a lot of our formulas as they're written over here are going to start with 1. And so if I give you something else that doesn't start with 1, I'm going to want to be able to find two summations that do start at 1, which I can use to get this. And the main idea here is I'm just deleting, subtracting away from the sum from 1 to n, the first m minus 1 elements. So the sum from 1 to m minus 1, I'm going to subtract each of those. And that's going to give me what remains is just the sum from m up to n. Now, what are some summation formulas? Well, if you sum a constant over and over again, 1 to n, that you're doing this basically addition n times, that gives you a times n. That's a pretty easy one. In fact, that's sometimes given as the definition for multiplication by n. Now, on the other hand, for summing the whole numbers from 1 to n, I'm going to want to times the number n by n plus 1 and divide it by 2. Regardless of whether n is even and n plus 1 is odd, or n is odd and n plus 1 is even, that's going to be an even number overall, and so dividing it by 2 will give you a whole number. There's a corresponding formula for k squared, right? If you sum the first n squares, you get the following: n times n plus 1 times 2n plus 1 over 6. And finally, and kind of curiously, when we sum the first n cubes, we wind up with the sum of the first n integers, but now squared. Let's see how we could use these properties to answer the question. The linearity here would allow us to split this into two sums. Summing 9s from 1 to 13 is just 13 9s. This is just a product 13 times 9. And then the cube function was n times n plus 1 over 2 squared, which gives us the same result as when we did it in the calculator. That's a good sign. And then over here, we want to take this and factor out the 4 as a constant up front so that we can focus on this k squared. This summation does not start at 1, it starts at 9. So we're going to want to sum from 1 to 26, and then we're going to want to delete the elements from 1 to 8. Plugging in these numbers 26 and 8 into these formula for the squares, and then taking a difference, multiplying by 4, we get the answer we got before. Number 39, what I might do is I might make a list on my calculator of the entries 1, 2, 3, and 4. Let's store this in our calculator as a list. So second one to give me list 1. And now what I could do is I could say, what are the elements in that list, factorialed, so my factorial is over here, divided by, let's put this whole thing in parentheses, the elements of that list squared, plus 5 times each element of the list, plus 7, and that will spit out some stuff. If I want to look at that stuff as a fraction, we could just store it as a fraction, which actually gives me some different answers than I had here, so I must have had a typo when I did this before. I was very curious, but I don't know where those numbers came from, but these should be our correct answers here. Question 40 asks us to find the 7th term in the geometric sequence. So first we want to get the model for the sequence, which means finding the common ratio, r, and the first term, a1, we can see that's -8. Looking at what we're multiplying by each time, we can see that's going to be timesing by 5 each time, and that gives us our common ratio, right? Divide 40 by 8 or divide -200 by -40, you're going to get a 5. So we're multiplying by 5 each time. And if I then want to know what is the 7th term, we plug in 7 into this, which will tell us, okay, we'll multiply by 5 6 more times and you'll be at the 7th position. And this gives us -125,000. Question number 41 asks us if this geometric series is convergent. Geometric series will be convergent if the common ratio is of magnitude less than 1. That is to say, if it's between -1 and +1 exclusively. So it can't be those endpoints, but this is a proper fraction, 7/8. That's less than 1. And so this is going to converge. Your formula for a convergent geometric series is given as such. And I want you to notice the indexing here. We either need to say that we're starting at 1 and we use the formula with an exponent k minus 1. But think about it, that's exactly the same thing as if I started from 0 and then just used k as the exponent with no -1. your exponents would still begin 0, 1, 2, and so on. And here, 1 minus 1, 1 minus 2, 2 minus 1, 3 minus 1, that's still the numbers 0, 1, 2, and so on in the exponent. So these two summations are exactly equivalent. And from our formula here, we can get that we need to take our initial term 3, and then over that put 1 minus the common ratio. So 1 minus 7/8 is 1/8, and then dividing 3 by 1/8, we get 24. So that's going to be the infinite sum of this geometric series. All right, that's going to do it for this part of the review. Thank you very much for your patience, and have a great day. Good luck with your studies. I'll see you in the next one.